can only make the model of the amplifier more complete if I did some selection. And I already have a lot of things to look at. I have an output voltage range and a swing that I need. I need almost a rail-to-rail output operational amplifier. I have a gain bandwidth product. I know about its noise. I can calculate the showstopper value. So we are going to select components and put it in this diagram. For the noise, I need RB, which is the parallel, which is this resistor, smaller than 600 ohm. I need the coupling capacitor to cause no impedance in series with the signal path for all signal frequencies, because it would enlarge the contribution of the equivalent input noise source. So this impedance should be lower than this one over the whole frequency range of interest. And that's why you find this, this should be F low, the lowest frequency, which is 100 Hertz. Showstopper values for the operational amplifier noise are found in 3 nanovolt per square root of Hertz and 5.25 picoamps per square root of Hertz. For the gain, for the bandwidth, there is this for the high pass, the low frequency cutoff, and I need a gain bandwidth product larger than 45 megahertz if I have no other contributors to bandwidth limitation. So for the accuracy, I need this resistor to be much larger than this one, so there was no extra attenuation. And I want to have a DC gain that is so large that it plays not a significant role in the midband inaccuracy. So I need to have, I have attenuation, I have a voltage gain that I want. So let's say if I want a 3% error or so, that's here, then you have 33 times 90, which is 3000 you need. For the drive capability, about 5 milliamps, this slew rate, and a saturation voltage from the positive and the negative rail of less than 0.25 volt. And then you go to the internet, you go choosing, and you see I did something. I selected the OPA 211. That is an operational amplifier that we have done before. And of course, you can select many others. I just wanted to do this one because this one has a very complex output impedance that causes all kind of nasty effects with this load impedance, and still we can get it stable and give it a nice step response. So here are the values that I selected. I selected 220 ohms for this, which is much smaller than 600 ohm. This one has 1 nanovolt per square root of Hertz and about 1 or 2 picoamps per square root of Hertz noise, which is far below, below the spec. We can view the data sheet later. This one is definitely a short at 100 Hertz with respect to 220 ohm. This one is much larger than 600 ohm, but does not cause a huge error for the bias current, which can be as large as 100 nanoamps, and 20K times 100 nanoamps is 2000. Nano is 20 microvolts, am I right? Something like 20 microvolts offset error, which is not really a big penalty from the output swing. Here, this should be a short with respect to 600 ohm or the whole frequency range of interest. And here, this one should be lower than 20K. So there's a lot of degree of freedom, of course, to select the components, but this is like, say, the motivation and the values I selected.